material plus the laser. I'm from the Aerosint, so we are based. So first of all, I will give a short introduction who is Aerosint and how we provide the solution to give the possibility to have multi-materials in this thin layer. And then I will show you two different case studies to show you how the industry is responding to the multi-material solution. So first of all, we are a company based in Belgium, in Liège. And then since last year, we were already part of the Desktop Metal from the States. So as I said, we are providing the solutions to the selective powder deposition. We are not a company who build up the printers. So we have to collaborate with different companies for that. So here, as you can see, we can really deposit the two different materials. So in this case, this part is the copper powder, and then the gray area is the stainless steel. So this is how it looks like, but I will give you more details how it works in principle. So as I mentioned, we are just very focused on the powder deposition technology. So we can combine with this technology with different manufacturing processes to produce different products for the industry. So for example, we established a very good relationship with Equiniti from Aachen. So our machine has been already successfully integrated into the MIDI Plus machine, which we also have in-house. And recently we just almost close to the end to fully integrate our system to their micro machine because the technology is still very new, so most of our customers are from the academia. So we also see maybe they just have a need for small machines, so the micro system would be a solution for that. And also another good news is that in the micro system, we are able to deposit 3 materials instead of the 2 materials. So this is the fusion-based additive manufacturing process. We are also active in the sintering-based AM process. Since we are acquired or part of the Desktop Metal, so it sounds logic to integrate our system to their machines as well. So we are also, by the end of the year, we will be able to finish the integration of our double material into the shop system. So they are not only doing multi-material parts, but also because in the binder jetting process, you always face the difficulty also to depowder it because the powder is relatively cohesive. So you can imagine that you use second roller to deposit material which is very have good flowability. So that's also an added value. So this is the die and the presser is very unique process that we want to use it for combining metal and ceramics. So this is only developed by us. So the principle is very easy. We use our recorder to deposit only the pattern, and then later on you put into the furnace or you put into the SPS to densify the parts, so you can really make them metal and ceramic. But of course, today's focus is on the LPBF process. So how does our machine works? I already heard many people were discussing about it. So here I will go to a close look. So the process itself is similar with the single LPBF process. You have the powder deposition and then later on the selective laser melting. The difference is in the first step. So instead of using a doctor blade to transform the powder, we have this, we call the SPD system. So it consists of 2 different rollers, and each roller you have like a mesh, and then the powder deposition is coming from the top. So the powder is just by gravity dropped on the mesh. There is a pressure difference inside and outside of the mesh. That's why the powders can be mechanically capped on the mesh. And then this roller can rotate, so you can really coat the entire mesh with the powder. So afterwards, you can transform this, move this entire system onto the build plate. And then at the bottom of the cylinder, we have an array of like valves, which you can locally control the opening and close to eject a pixelized powder. So that's why our pixel size is around 500 micron at the moment. We are also working on to upgrade to like 300 micron. And since this like Y direction is limited by the length of our roller, so we are at the moment we can only do 96 millimeter on the Y direction. X direction is not affected, and the brake coating speed is lower than the single material LPBF, but that's we will also be able to upgrade. So we already have run internal test which can run up to 300 millimeter per second. As I mentioned, so in the current state, we have two materials in the midi plus and two materials will be in the micro. So since our system is independent of which powder you can use, once it can flow, it can eject it, it will be compatible with our recoater. So actually here I've prepared a video which you can see the process. I mean, otherwise you can also find it in the YouTube. So let me check if I can play it. So in this case, I have example of heat exchanger, which is okay. It's not played, but anyway, I will explain it. So. In this case, I also have the heat exchanger. If you later on have an interest, you can have a look at it because I will not pass by it. People are sitting apart. So in this case, we have the steel and the copper. So this is very interesting to the industry because of the thermal conductivity of the copper and then the mechanical strength which is provided by the steel. So with our recoater, we can deposit the two material on the layer. And since these two materials have requires different processing parameters, so we have to lace them separately. So in this case, we always lace the steel and then followed by lacing the copper. So now I will give you more like details about the two cases that we are working on in the company. So as I said, the combination between the copper and the steel are very interesting. So one example is the injection molding industry, where the M300 material is very, let's say, popular and mature for LPBF process. And then we chose the copper chrome zirconium, which is also optimized, or let's say developed also for the LPBF process with the infrared laser. And then the advantage, of course, we can maintain the complexity of the ports which is given by the LPBF itself. You can see here we have the cooling, conformal cooling channel running through the copper, but you also, I call it conformal like insert. You can really control also the cooling rate locally of your inserts. So everyone, I think, is curious about the microstructure of the ports. Here it's really during the first DOE of this material set which we produced. As you can see here, there are two different types of interface, so the horizontal one and also the vertical, which is parallel to the building direction. So what we found out is that if we stack the M300 on the copper alloy, of course, the first few layers we have lack of fusion defects, simply because our parameters for the bulk were developed when the material is on the steel build plate. However, we do see very promising things. So if these two materials are well intermixed at the interface, as you can see here, due to the different contrast from the element. And then, of course, logic thing is that, okay, because the first few layers, it requires different energy density, we also did a trial to use a different energy input. So actually we found a very interesting result. We can really remove all these lack of fusion defects. So this work was really collaborated with the university from Liège. And then, since we are industrial company, we have to go for like also the property characterization. So here we really use a single heat treatment to not optimize but improve the property of both material at the same time, because the heat treatment could be also a big question, right? So as you see here, the margin steel, it can really increase from 41 to like 54, which in this range already meet most of the application in the injection molding. And at the same time, we tripled the thermal diffusivity of the copper alloy. If you are looked into this, because I also give thermal diffusivity of the margin steel and copper alloy, in this case it's half-half. So you also, they are very close, but actually the value they also increased by 50%. So now I'm going to give you a second case study which we conducted. So combining the copper and steel sounds very obvious, right? But not so many people are thinking about combining the materials from the same family or different titaniums, or even here in this case we chose the Inconel M316L. So the reason why we chose it is not only because of the combination of the different properties, but we also find out that these two materials have relatively wide processing window, and there is an overlap between them. So in this case, our powder bed is two materials. However, our scanning is we treat it as one material. So we really use the bidirectional scanning across the interface without changing lasing parameters. So it's a work in collaboration with Expert Tenoso Technology, and they are providing like algorithm to speed up the DOE process, and the goal is to really get the process more productivity, which means like use less time to produce a certain volume, and also shorten the DOE process. So how it works, it's quite simple. So you either the software will give you starting parameters, or for the materials which already have been started by the others, you can look into the literature values, and then you load into, then you go to multi-material LPBF process, and then you do the analysis just to check the density, and then you give the results feedback to the software, and then with the existing results, it will suggest you other parameters, like in this graph you can see. So the dark red color is with the high probability, so the software suggests, but you still see other like discrete area. It also needs data input. So what we have been changed is mainly the laser power scanning speed and the hatch distance, because these are the three main parameters also very relevant for the productivity. So as I listed three parameters which we use, so you can see that at the high energy input, we have quite defects on both materials. And then in the middle, it's the low energy side. The stainless steel looks fine, but in the Inconel, there are still some like defects. But at the C parameters, intermediate energy input, we can see that both materials are dense. And then this set of parameters gives the highest productivity as well. So here, as I just show you, this is my cross section, where you can see like the interface between, you have three different types of interface, and these two materials are relatively compatible compared with copper and steel. So you can see there is a sound bonding between all the materials. So now it comes to my conclusion. So I hope that you are convinced that we can use multi-material LPBF to build parts. And then you can also think about more other applications also from the research perspective, and to really together with us to generate more knowledge and then also industrialize it. So now I'm happy to take any questions.